Hello and welcome to the Scan&Solve Pro Webinar debut. Today I will be walking through a few of the new features on Scan&Solve Pro that were not previously supported by other Scan&Solve models, as well as just demonstrating a couple good simulating techniques for setup and analysis. To aid in this process, I've created two models, one a vice simulation, which you see now, and the other will be a kayak frame. So to simulate on the vice model, the first step is to think about what you want to simulate. So as we said before, Scan&Solve Pro allows you to simulate on multiple components that are all in contact. So each of these are individual pieces in Rhino, and they're all touching each other. So what this does in Scan&Solve Pro is Scan&Solve Pro will read this, and it will see that these pieces are touching, and it will simulate as if they were welded together or glued together with an epoxy. So the simulation I want to run is to simulate the vice clamping some object with full force, so it cannot clamp anymore, and someone continues to turn on the handle of the vice. So if I were to do this, there'll be a torque that's generated in this area here. However, the way it's set up right now, Scan&Solve Pro will read this all as connected, and that torque will just be generated to the vice body. This is not what we want, so before we simulate, we're going to have to separate the part that we want to simulate on, so that's no longer glued or welded to the vice body. Now that we've done this and we've thought about how we want to simulate, we're ready to begin setting up. Scan&Solve Pro can be entered into the command line, and this will bring up the scenario selector. The scenario selector is brought up because multiple simulations can be saved in Scan&Solve Pro. This is a useful feature if you want to run, say, 10 or 15 simulations on the same components. You can save the results instead of having to repeat the simulation every time you want to view in older results. So I'll start a new one. And the first step, once you're in the interface, this is the Scan&Solve Pro interface. This is where all the initial conditions will be set up under the Specify tab. The first step is to add your components. You cannot add restraints or loads until the components have been uploaded into Scan&Solve. So there are three components to the sections I'll be simulating on. The first being the handle and the shaft of the vice. And this will be made out of a stainless steel, something a little bit more ductile. A common steel used will be 302. The next component to be added will be the vice head. This will be something that will be a little bit more brittle and strong. A common vice material is cast iron. So I will use malleable cast iron. And the third component that needs to be added is the wood. So I want to find something stiff, and I'll get into these properties a little bit more shortly. But I'll use yellow birch. And I'm just going to select a wood grain, and I'll get into these more as well as we move forward. But for now, I'll just leave it simple. And you can see that we now have added each of the pieces as they're highlighted as I go over them. And just to make sure I have everything added, I can hit Add one more time and highlight the full piece and hit Enter, and there's nothing else left to add. So now it's time to add the restraints. So when thinking about what section I want restrained, when this vice is fully clamping on an object, there'll be a torque as the handles are load is continuously applied on the handles, turning it. But the friction inside of these grooves will dissipate that force in this area. So I'm going to restrain it around here. Next, I'll add loads. So there are two loads that I want added for the simulation. The first will be the torquing load, and that will be applied on the handles. So I'll select torque, and then I have to select the axis and the load amount. I'll make the load about 200 inch-pounds. This is a pretty significant load, but it's better to simulate on extensive loads so you know that it's safe rather than underestimate the type of load that will be applied. And then you have to choose the direction, or the axis, for the torque to be generated around. So I want it to go down the middle of the shaft. So I'll use my O-snaps here to get to the center. And I'll make the axis just running down the middle of the shaft. And you can see a nice visual of what we have just created. And then I will add a second load, and this will be the reaction force from whatever object is being clamped by the vise, and they'll be acting on this face of the wood. To simulate that, I'll use a scalar force. And for the metric users, I'll change the units to newtons. And I'll make that, say, a 9,000 Newton force. And the nice thing about scalar force is it will generate the direction that the load is applied, normal to whatever the surface is. So you can see I have a curved surface here, and the scalar force will be generated normal in every part of that surface. So this pretty much concludes the setup for this specific simulation. If I wanted to add gravity, the effect of gravity, I could check this box. However, I don't see it playing much of a role. The final thing is change the resolution. When determining what resolution you want, it's helpful to analyze the grid. This is the solution grid that Scan&Solve will use to compute for the simulation. And by increasing the resolution, the elements used to compute will gradually get smaller. And as the elements get smaller, your simulation results will continuously improve. However, the time that it takes to run the simulation will also increase. So you want to find a nice medium between the two. A general rule of thumb is to analyze the grid and find some of the smaller cross sections that you're simulating on, and make it so that the grid has about 3 of these elements per given cross section. So this looks pretty good. It doesn't have to be exact; just about 3 is a good general rule of thumb. So this simulation is now ready to run. Typically, I would click Go and let it load. However, I have already ran the results, so we do not have to wait for it to load. So here are the results for the vise simulation. Right now, we're viewing total displacement under the View tab. And we can see the areas that are red indicate larger displacements. To find the area of maximum displacement, I can simply click Max, and it will show me both the location and the magnitude of displacement experienced. So it looks like it's about 0.025 inches, which seems to be a pretty safe amount of deforming. I guess it depends on how you're engineering it to work, but that seems pretty safe for most purposes. As well, another feature you can use is to slide the deflection tab, and you can kind of see how the material will deform. And this has been implemented in previous Scan&Solves as well. But for those new users, this is a nice tab to kind of analyze how the material will deform. So some other features that are really useful, especially for analyzing stresses and strains, would be the section tab. Let's change from displacement to danger level. The danger level is currently set at a maximum of 1, and that represents the yield strength of the material. So if it exceeds the yield strength, that will be displayed as red if the material yield strength is exceeded. So I can hit the maximum to see what kind of danger level I'm looking at, and it looks like I'm just below the 1 marker. So this is cutting it pretty close. If I was actually going to be applying these loads, I would probably want to change my geometry so that the cross-section in the shaft of the handle is slightly thicker. By increasing the cross-sectional area, I should be able to decrease the danger level, allowing for a safer use of the vise. Also, another way to view this would be using the section sliders. By enabling this, it makes a cut inside of my simulation, and I can slide this marker to view different parts. This is really useful if you're analyzing something like a tank or something that is covered so you don't have a great visual view of what you want to see. So this pretty much sums up the vise simulation. I have set up. And now I'll get into a couple more advanced topics with my kayak simulation. So the kayak frame is already built. A frame like this is commonly covered with a nylon skin to be made into a kayak. So what I want to simulate is how this wood will react when a nylon skin is covering the wood and applying that compressive force. So I'll start by opening up Scan&Solve Pro. And the scenario selector is once again opened. So first things first, we have to add our components. When adding components, you can add multiple at the same time, but there has to be two conditions that are satisfied. The first being that all the materials have to be the same if they're going to be added simultaneously. The second is that if it's wood, they have to have the same wood grain orientation to be added simultaneously. Wood grain will be the same for flat wood for me, so I can add all flat pieces of wood. You can see that some of the stringers along the side of the kayak are curved, so I will add those separately later. So I'll start by adding the individual pieces of flat wood. You can see that along the seat, there's no curvature in any of this wood. As well as in the cockpit, some of these side rails are flat. And the final things I want to add are going to be the keel of the boat and the side supports. And you may be thinking these side supports are curved. You can see the curvature going on in them, and that is true. But if you think about how this kayak would be engineered, these side supports would be made from plywood, and plywood can be simulated as flat wood. So I can go ahead and add all of these side supports as well. And also, the stern and the stem of the boat will also be made from plywood. So these will be added as well. So this brings up our material selector once again. So I know that kayaks are commonly made of cedar, so I'll select the western red cedar to be my material. And I want to quick go into what this table is representing. So this is the material mechanical properties, and this is really what Scan&Solve uses to compute the different materials. These are the main mechanical properties used. So there's the density, which is pretty self-explanatory. And then you'll see in E, followed by three different subvariables, in L, a T, and an R. So the L represents the longitudinal grain direction. The T is the tangential grain direction, and the R is the radial grain direction. Wood is an orthotropic material, so it will react differently to forces dependent upon the direction of the load. To help explain what these grain directions are that I'm talking about, I have a picture. So if this is a block of wood you're simulating on, the red arrow would represent the longitudinal grain direction. This can also be thought of, if you're looking at a tree, the vertical or axial direction the grain is running. The blue arrow in Scan&Solve represents the radial grain direction, and this would be if you're in the middle of a tree, moving outwards towards radially along the grain, and the green arrow is the tangential grain direction. And as I said before, the material will react differently dependent upon the direction the load is applied. And you can see that each of these have different mechanical properties. So the E is the Young's modulus, or stiffness. The V is the Poisson ratio. The Poisson ratio, it's the negative ratio of axial strain to transverse strain experienced by a material. And this can be thought of in simpler terms of if you had a steel beam, perhaps, and you were applying a tensile load axially, so you're stretching the beam, a process called necking would occur, where around the middle of the beam, the sides would start to shrink or compress inward, and how much that secondary strain is experienced is dictated by the Poisson ratios. And lastly, G is the shear modulus, which represents the stiffness of the material in the shearing direction. So now that we know what these properties represent, it's time to select the wood grain direction. This is another slightly more advanced topic as well, but it's pretty important when you're simulating on wood. So for flat wood, there are three common options: the rift sawn, the flat sawn, or the specify option. And I'm going to bring the picture back up. So this is a picture of rift sawn, and this is a picture of the flat sawn. So when these two options are selected, Scan&Solve will read the geometry and compute the wood grains for you automatically. So it will read the geometry of your component, and it will assign the longest side the longitudinal grain direction, which is the red arrow. And that's the same for both rift and flat sawn. Now, if you select rift sawn, it will read the geometry for the middle length side, and it will apply the radial grain direction along the middle length side automatically. And the shortest side will then be given the tangential grain direction. However, if you select the flat sawn, the middle length side will be the tangential grain direction, and the shortest length side will be the radial grain direction. If you don't want either of these two, you can specify your own grain direction, where you can angle it or you can change the directions however you desire, and this has to be done manually. So I'm going to use flat sawn for my flat pieces of wood, and I'll apply this. And I'm going to pause here. This was a good amount of information. So I'm wondering if anyone has any questions. We'll take a look to see if there's anything we can answer before we continue on. Just go ahead and type them into the comment box if you do. So we have one question, and that is, how long did it take to run the VICE example simulation? And the VICE example, I'll bring it back up, was a pretty quick simulation, mostly because there weren't many pieces. The more components you add, the longer it will take. I would say that this simulation took about maybe 3 minutes or so, and I actually may be able to, sometimes it shows how long it took to run the simulation. Yeah, so we can see it took 2 minutes and 13 seconds to run this VICE simulation. So it was pretty quick, but like I said, there weren't too many components going on, so it was a pretty fast simulation. I'm going to pass over to Michael for the next question before we continue on with the simulation.
So one person asked whether the only orthotropic material is wood. Currently, the only built-in orthotropic material is wood, but we will be adding support for composites later, because I assume that's the question you're really asking. For now, you can actually enter a composite material as a type of wood. You can sort of fake scan and solve it. It doesn't know the difference. Internally, it operates the same way.
So we'll give it just another 30 seconds to see if we get any more questions in before we continue on. So a question asked is that we have rendering displaying the wood, and they're curious to know if this rendering is an accurate display of the actual grain orientation, such as these pictures. These pictures, we rendered it so that it does display the grain direction well. However, when you do this in Rhino, we do not yet have the capability for the rendering of the wood to be assigned in the grain direction. But we do have techniques for displaying the grain direction, which I'm going to get in shortly after the questions are concluded. Okay, so I'm going to conclude the temporarily for now. We'll have more time for further questions. But so going back to that last question that was just asked about the rendering of the wood and the grain orientation. So the rendering does not accurately display the grain orientation. However, if you go to the Settings tab, you can turn on the material CSYS display, which is the coordinate system. We'll come back to this shortly, I guess. After I apply the curved wood, we'll come back and look at it in full. But this will display the wood grain directions. So moving forward, the next step is going to be to add the curved wood. This should be everything left that I've not already added. so I can highlight everything and hit enter. The technique for adding curved wood is by using the guide option. However, when you hit guide, it'll ask you to select the guide curve and later the guide surface. And we do not yet have this. This has to be manually created. So I'm going to walk you through quick on how to create this. So by hitting the done option, it will save everything that I have entered into Scan&Solve. So I don't have to worry about losing any of my data. And now we're going to make the guide curve and guide surfaces. And really there are two techniques that I use for this. The first I use if I only have to do maybe one surface or a few surfaces, or if I have a lot of complex surfaces with no symmetrical geometry. You can see that this has a lot of different components that need to be created for guide curves and guide surfaces. And it does have symmetry, so I will not use this option. But just to quick let you know how it's done, I'll use the command extract surface, and then click on the surface that represents the curvature of the wood well. And I'll just pull it out so you can see it a little bit better. And then for the curve, you go to curve, curve from objects, duplicate edge, and then you'll once again select the curve that you want extracted, and I'll pull it out just so you can see that better as well. So you can see now that these are the curve guide, the guide curve and guide surface that will be used for grain orientation. However, I don't want to do this for each individual piece, so I'll show you an alternate technique. So I'm going to use my layers, if you're familiar with Rhino, which I'm assuming most people here are, which will come in handy for organization purposes later. But for this next technique, I'm going to start off by using this curve from objects duplicate edge once again. And I'm going to extract all of the curves of each of these wood planks that I want to be represented by a guide curve or guide surface. And when making this kayak, it's made by piecing some pieces together, and this is why the curves are being duplicated individually. So we'll just take a minute here. Okay, so this looks like all of the guide curves I want extracted for half of the kayak. But I know that symmetry exists in the kayak, so I can only do half, and then I can mirror the mirror for the second half. So I will hit enter, and I've extracted these. And now I'm going to turn off my default layer, which is the kayak. So I only have so now I only have these curves. So now that I have all my guide curves, I am going to create the guide surface. And the way to do this from these curves is just to highlight them all, go to Surface and Loft. Now when you're doing this, Scan&Solve Pro can only read NURBS curve. They cannot read a poly curve. So to do a loft, you need to make sure that you have the uniform option set up, as well as the rebuild option checked. And when you click OK, it will create the surface for you. And just to make sure that it is a NURBS curve, I can hit what, and you can see here, NURBS surface, and this is what we want. So I now have half the kayak set up, and you can see that this is a good representation of the curvature of the kayak, since that's what it was made from. So now I'm just going to mirror this, and I'll turn my kayak back on to get my mirror plane. I want it right at the halfway of the kayak, which I know is going to be halfway through this keel. So we will take the mid, and we've now mirrored it through there. And now we have our guide curve and guide surface for all of these outer stringers. And we can go back to Scan&Solve now, and we can add all the we can now add the curved wood. So I'm going to highlight everything because it's the same material. Cedar Western Red again, and I will use guide. And I will walk through one by one and ask me to indicate the guide curve and surface. And since I already have all of these set up, all I have to do now is just click the curve and the surfaces. And you can go through this pretty quickly. And it's easy to accidentally click the wrong curve or surface, so you do want to take your time and be careful. Make sure you're getting everything correct. Okay, so now all of the guide curves and surfaces have been set up, and I will hit apply. So now we will go back to our setting, and we will look at the material coordinate system. And you'll see that these arrows appear. And these arrows are the same as from the pictures I was showing you before, where the red is the longitudinal grain direction, the blue is the radial grain direction, and the green is the tangential grain direction. And you can see to what we did, by looking at following the red arrow, you'll see that it curves along with the wood. And you can kind of see just how much by looking at the angles between the two different sides. And this is ideal. This represents steam bending, which is a common engineering process for building with curved wood. And it provides some maximum mechanical properties, and this is how the kayak would be built in real life. So this is an important process to understand and be able to use. To help clear things back up, I will return to my default layer, and I will hide the guide curves and surfaces. And I will turn off the material coordinate system once again. So now all of my components should be added, just to make sure I can highlight everything. Okay, that's good. So moving forward, so I mentioned earlier that some of the pieces in here are plywood, such as these side supports. Plywood has slightly different mechanical properties. So another useful feature, I'll just do a quick walkthrough, is customizing material. So if I hit this custom button, and I go to Pseudo-Western Red, I can hit copy. And it'll copy all the mechanical properties inside of this table. But now I can edit them and create a new material, and I'll just add ply. So I know that this is my plywood. The research on what the mechanical properties are for the plywood of this version. So I'll just go ahead and add those through real quick. If there are any questions while I'm doing this, this would be a good time to go ahead and type those up now. I'll go ahead and pause after I finish customizing this material, and we can answer some more questions. Okay, Michael's going to take another question while I'm finishing up adding this customized material.
So I see there's a question about simulating spring back in a curved piece of wood by specifying grain direction with no restraints or external forces. We can't do that right now. That sounds like an interesting capability, though. I'm not exactly sure how you would do that. It will probably require specifying displacements instead of forces. What you could maybe do instead is specify the grain in the straight piece and then try to apply forces to it to get it into the sprung or into the bent location. But I'm not exactly sure how you would do that right now with what we have. So go ahead and keep asking questions if you have any. It looks like Ben is almost ready. Okay, I'm going to switch over to Ben.
All right, so we're going to conclude the questions temporarily again and continue on. So now you can see that I've just created this material property, this material itself, and it now shows up into my material selector. And this will be permanent until I delete it. So this will stay in here. It won't disappear when I open a new version of Rhino. So this is permanently in here. And To delete it, you just go to Custom. You can select and you can hit Delete if you so choose. But for now, we will continue. So I'll add the plywood to that side support. And I did this for each of the side supports, but for time purposes, it's pretty self-explanatory. I already have the simulation results once again. So for the actual simulation, I did it for all, but for now, I'll continue on. So now it's time to add the restraint. So you have to think about where you want the restraint to be added. When the skin is applied, it will be covering almost all of the kayak, and the force will be distributed almost on all of these surfaces. However, the seat should remain unaffected. So I will go ahead and go through and add it to the seat as my restraint. No force should be transferred to the seat, and no deformation should be experienced. Okay, and the next step then would be to add the load. So I want to add the load of this skin, and this can be a bit tedious. So I want to add it on the outside of each of these wood planks, of each of the stringers, because that is really where the force of the nylon skin is going to be making direct contact with. And you can see some of these planks are a little bit angled, so for that I'll hit both the top and bottom because they'll both be getting a little bit of that force. And typically I would add this for the full kayak, but for time purposes, since it's pretty repetitive, I'll just do half the kayak. And you can just imagine that I covered the whole kayak. And once again, for the actual simulation that I've already set up and ran, the full kayak has been selected. We'll get some parts of the top here. Looks like that's already been selected. Okay, so this is half the kayak, and I'll leave it at this, but imagine that the full kayak has been selected. And this is pretty similar to previous scan and solves, maybe with a little bit of a different interface. But it gives you your options for what type of load you would like to apply. And for newer users, real quick, I'll just go into a little bit of detail. A vector force, there are two options. This will just be a force that's applied, and you can either type in the X, Y, and Z components of the force, if you want to break it down that way, or you can type in the total magnitude of the force and just draw your direction manually in Rhino by clicking the direction tab. Either of these work, and it will split the magnitude of the force, the load, evenly based on area of the different components that have been selected, unless per face is checked, in which case each face that has been added to this load will get that specific amount of force applied. There's a scalar force, which we used before, which the direction is always normal, either inward or outward, depending on whether it's positive or negative. And this is just a single force, similar to the vector force, without the direction. Pressure, which is what I'll be using, which is a force per unit area. And I'll go ahead and set that up now. So I'll go ahead and switch into metric. And I'll make my force to be split up 5,000 pascals, which is a pretty hefty force. And you can see here how it's distributed. And if I would have highlighted the whole thing, you would see these equal arrows coming from the other side as well. A pressure expression is almost the same as a pressure, except it allows you to add an equation that will change the pressure depending on location. There's the hydrostatic option, which is kind of a simulation of liquid weight. For example, if you fill the pool with water, the side walls of the pool would be experiencing a hydrostatic force. And the way this is done is you add a density. So for the pool scenario, you'd add the density of water, and then you draw a plane, and that would be a representation of the top level of the water. And it would imagine if you had a pool designed in Rhino, that it was filled with water, and it would apply that force for you. And then there's a torque, which we also have already demonstrated, which is just a twisting force. So I'll go ahead and hit OK. This load is ready, properly set up. So the kayak is almost ready to simulate. Once again, I'm going to leave gravity out. It should play a pretty minimal effect. Just a few last things to touch base on. The resolution. Once again, we now know we want about 3 of these elements per cross-sectional area, and we're pretty far from that. So let's see what this looks like. Okay, it looks a little bit low still. Yeah, so right around here looks pretty good. You can see most of them have at least 3 elements. If some miss, like this maybe is 2.5 only, that's okay. It should still give good results. And you can also test for convergence. There's a blog post on that on the Scan&Solve forum as well to help you do that. But this is a pretty safe rule of thumb. So I'll turn off the grid. The last thing I want to just touch on before we go into the results of the simulation are going to be these different linear solvers. So these give you some freedom on how you want this solved. They should all give pretty accurate results. The SnS solver is the default solver, and that's what I use. It's the slowest solver, but it uses the least amount of memory. And this is beneficial if you're simulating on something with where you increase your resolution to a large element size to save you some memory on your computer. The ISS solver is the iterative solver. It's slightly faster than the Scan&Solve solver, but only slightly, and it uses only slightly more memory. So they're pretty similar, just a little bit faster and a little bit more memory. Like I said, about the same results. The third solver is the DSS solver, the direct solver, and this is significantly the fastest of the 3 options, but it does use significantly the most the most memory, I'm sorry, and it's only recommended to use if you're simulating on something less than 100,000, with 100,000 elements for the resolution. And this is the precision. This is very low. I typically run mine at about 1 times 10 to the 9th. And this is, I believe, actually what the default setting is, 1 times 10 to the 9th. It looked like something got tampered with a little bit, which is why that was missing. But that pretty much sums up most things, the setup for running the simulation. So now we're ready to hop into analysis, which I already have ran. And we can take a look. So now we're viewing total displacement. We can see the location of maximum displacement. And the amount, it looks like it's about 1.6 inches, so that's a pretty significant deformation. But I did add a pretty significant load as well. And we can see how the material deforms. And you see it's kind of crumbling up on itself, which is what we expect from a skin being applied across in every direction. And we also see that it bends upward, which may seem a little confusing at first, but if we think about what we did, we added a pressure, which is a unit force per area, and it's split evenly based on the area. If you look, most of the stringer's area is at the bottom of the kayak. So we have more force going upward than we do sideways. So we get the results that we would expect from that. We could use the section tab, but we've already gone into that. So one other thing I want to analyze is the stress in the XX direction. This gives pretty interesting results. So it doesn't look like much at first. This is the stress in the XX direction. But if you play around a little bit maybe with the legend, you can find something more interesting. So I'm going to slide this until, let's see. Yeah, okay, so this looks like a pretty good cutoff. If you look now, by adjusting legend, if you look at over on the left at the color schematic, you'll see that it goes from negative, where it's negative, the stress is negative, is blue, and it turns positive in green, and yellow and red are also positive. And what this means, in areas that are negative, the kayak is in compression, and areas that are positive are tension. So now if we look once again at the deflection, turn that all the way up, we see this bending going on here. When bending like this occurs, what we would expect to see is tension on the bottom side because it's being elongated, and that is exactly what we do see. Bring this down. So you can see the green, the yellow, the red, that's all positive. So this area is all in tension. And if we look at the top, this is kind of being pushed together. So we'd expect to see compression, which is what we do in the areas of bending. We see darker blues, all negative numbers representing compression. So this is pretty useful when building to know where your material will be in compression and tension. If you're dealing with brittle materials, you know it's more likely to break in tension, so you got to be aware of that. So this mostly sums up the viewing page what I wanted to go through. The last two things I want to touch on are the bake option and the report option. So the report, if you're not familiar with Scan&Solve, will put this into an HTML. It'll put your results into an HTML. It'll bring pictures with it. It'll describe the setup, and it'll kind of just put all your results for this simulation into an HTML file, which is pretty nice. And the bake option, which is used to output these results. And you can export it as a Rhino mesh object, a VRML, a STL file, or a PLY. And when you do this, the rendered coloring that is now applied, demonstrating the areas of tension and compression or maximum displacement or whatever you have set, will also be exported with this bake option. So this is just another way to export your results. So that concludes what I have prepared to talk about, and we'll once again open the floor to questions. So feel free, go ahead and type in any question that you have at this time. Okay, so it looks like one of the first questions we have is about the Specify tab. So I did not mention that. Let me go ahead and see, give you a quick demonstration of what that is and what I'm talking about right now. So if we open up Scan&Solve Pro, and we go to, let's just edit. So if we were to edit this wood material, we can, see, we made this yellow birch. There's this specify option, which I didn't describe it in detail at all. And what this is it allows you to customize your own wood grain. So let me hop into a new view. That perspective can kind of get a little tricky when specifying your directions. So ask you to choose your long grain direction, which is your longitudinal grain direction. So I'll just throw that in an angle. And your radial grain direction, and I'll throw that down here. And it will compute the tangential from this information. So I'll hit apply. So now if we look at settings and we turn on the coordinate system, if we look at the wood, now it's on an angle. So this was not an option from flat sawn or rift sawn, but I've just customized my own wood grain to be how I want it. It's also commonly, you also have to use it if, let's say, your material is a cube or has two sides that are equal length. Scan&Solve can't assign the radial or tangential grain direction if it doesn't have one side longer than the other. So you'll have to use the Specify tab for those situations. Okay, so someone asked about me selecting the this only stringers on one side during the setup, and how come the results in the simulation look differently, and that is because I set this up earlier, and I ran it so we wouldn't have to wait for the runtime. And when I set it up for the actual results, I did it properly. I applied the forces across the full kayak. Just to save time for this example, I left it at halfway, but I never did anything with this example. This was just showing you how to properly set up and apply the initial conditions. And this was a full separate simulation where it was done properly, and I applied it to the full kayak. Sorry for confusion on that. So we have another question on, I believe it's glass fiber laminates, and they're wondering if we can run simulations on that. It is something that we are currently working on. With Scan&Solve Pro Beta just being released, the beta version, we're still working on, we have a lot going on, but it's on our to-do list. And if you know the mechanical properties of the laminates, you can add it yourself. It is on our to-do list, and it's one of the next steps we'll be taking to improve Scan&Solve Pro. So to put a time frame on composites as well being added, we're hoping to aim for maybe around within the next 6 months or so, maybe sooner, maybe a little later. But it is one of the most pressing things on our to-do list. And we will hold an additional webinar when the laminates capability is released as well.
Okay, I see your question about the scripting language. The scripting language we plan to use will be Rhino Python. It's not implemented yet, but that's what we will be adding. Hopefully that fits in with what you're looking for. If it's not, just let us know. Okay, there's a question. If you posted a text file for a material, can you show how to load that into the library? Okay, Python sounds good. Okay, so I can show you how to import a file or import a material file. Or Ben, have you done it? You probably have not done it. Okay, I'll show how I will demonstrate on mine how to import a material file. So on our website, we actually have several material files that you can download. So if you go to the support tab and go to the downloadable resources, here's additional materials that can be imported into Scan&Solve, either 2014 or the Pro version. So what I will do is actually select one of these, and I just downloaded it to my downloads folder, and it's right here. So if I run SnS Pro and I want to add a custom material, I go to the import option because I'm on the isotropic material editor. You can import, and I will choose from my downloads the American supplemental metals. And if you want to see actually what this looks like, it's just a couple of materials. It's aluminum 5052 through a variety of steels. So I choose that and then choose open, and it imports it into, it should have imported it, I guess. I think it's here. Yeah, it just added them at the bottom. And if we go here, you see that I've obviously got the next version that I'm working on. It should have loaded them down here at the bottom. Here you see them, the ones that were just added. Does anybody else have any questions? Seeing none, I guess this will conclude the webinar. So if you have any questions or any questions you come up with that weren't answered today, please email us at info@intactsolutions.com. Thank you.